Well, this is incredible. We're sitting outside Bucks in Woodside. So we're going to San Francisco today.
That's right.
I was going to say, let me know when you're in autonomous mode, then I could
Right.
be less concerned about my safety. We have the only stack in the world that has a end-to-end
That's right.
AV stack,
That's right.
as well as a traceable, human-engineered
That's
AV
right.
stack.
That's right. Which is very critical because, for end-to-end model, it's very difficult to verify. Basically, it's always safe, right?
That's right.
And the classical stack is developed based on the, let's say, protocol and the process. We know how to ensure safety software.
Yeah, the thing that's a miracle about Alpamayo is that it does amazing things.
Yeah.
And it drives like a human.
That's right.
Because it's end-to-end, whenever there are things that needs to be improved, you know that you could back-propagate that through the whole model and you'll improve it for sure.
Yeah.
I think the challenge, of course, is Alpamayo is as incredibly smart as it is, and it can reason about the circumstance. We don't know what it can't do.
That's right. Yeah.
And so that's the challenge, and that's the reason why our classical stack is so incredibly important.
That's right.
The thing that's really great about Alpamayo and our stack is that I don't ever feel that Alpamayo would ever be allowed to do something that is out of distribution. And the reason for that is because our classical stack gets involved and prevents it from happening.
Right. One thing great about our module is that the development speed is just amazing. We have iterated, right now the version is, I think, 2300. We labeled based on the number of iteration we have, essentially. And roughly speaking, we have, this is roughly over a year, right? So we have, in average, like 7 models being iterated every day. Obviously, not every single one of them make to the car. But because this process is, just imaging and trajectory out, there's the manual steps in between in the development process are just minimal. That's why we can iterate super fast.
Well, the thing that's really great about end-to-end models is that whenever you're improving the model, because it's one giant model that's end-to-end.
That's right.
You're not going to fix one thing and break something else. The classical models, because there's so many different modules, you fix this one thing.
The logic sometimes contradicts with each other.
That's right.
Yeah.
And so it's so brittle, and you fix one thing, you're chasing cats and dogs around the table, and it's really hard. Most control systems, which are built the classical way, have the same problem.
And it has so many steps. For example, right, today we actually going to see speed bump, based on our module. If you think about how do you detect speed bump and react to it properly, you have to break into many, many steps, start from perception, and it have to be added in the word model, in the context fusion, and then basically you have to decide how early you have to slow down, by how much, and maybe even based on different speed bump, you have to do things differently. But with the end-to-end model, it just basically just happens. Actually, we didn't even plan for it, just happened.
Yeah, right.
So it's pretty amazing.
There's so many people building end-to-end models.
Right.
But I really think that it's the fusion of the two.
Yes.
That's revolutionary. That gives you
Yeah.
the superhuman, the amazing driving capability.
And the safety.
And the safety.
That's right. Back to the model, actually, it does because it's so big, right? Actually, we do see sometimes, when you try to address something, it have some, something else might get regressed.
Right.
So being able to establish a basically full-blown, very comprehensive, basically closed-loop evaluation, what we call CLE, is super critical. This is how we gate our model to make sure sort of the bad babies get filtered out.
The thing that I still love, though, and I think this proves to be true, that even when you have a regression on Alpamayo, your classical stack would always guardrail it.
That's right. Actually, that's why basically, our development speed has been so good, because you always have a backup, essentially.
That's right.
Even the model has minor hiccups,
that's
it's okay.
Right.
We will keep iterating and just keep getting better.
You never have a loss of safety. You have a loss of capability, but not a loss of safety.
Yeah.
This is going to be so critical for our Robotaxi. when that happens. You know what I'm saying?
That's right. That is the advantage we have as well as we move into L3 and L4, because we have redundant stack even L2++ to scale it basically for L3 and L4. It's just so natural.
That's right. Yeah, that's critical. And then there'll be the teleoperations, right, as a backup system. And then, you know, every robotaxi, every robotaxi service should have, you know, a air traffic control center. And the thing that's really great with our technology is that, for whatever reason, if the robotaxi were to get stuck, all you have to do is give it a couple of waypoints, the human injected waypoint, and it should be able to navigate itself right out of it.
Right.
And and because it has a safety stack, a backup stack, no safety would ever be jeopardized.
That's right. And the other thing our Mayo does really, really well is lane change capabilities. Because the classical, when we do lane change, we have to select a gap. We have to do a lot of basically rules and heuristics, essentially, to make sure it's safe. So sometimes it's a bit timid, essentially, when you have, you know, cars in the front, you have cars in the back. Basically,
there's so many rules.
That's right. Yeah. And the Mayo, basically in the city, it's just doing an amazing job in the lane change. It's also very human-like, essentially, and never give you the feeling of rigidness.
Well, it imitates the human from all the drives that it's been on, and then it generalizes from that.
That's right, yeah.
You know, the basic concept of deep learning to essentially memorize and generalize works just fine for a self-driving car.
AI is the single most important technology to make self-driving possible, essentially, right?
Yeah.
But you know, I have been working on this, obviously, as you know, for a long time. But the last 2-3 years, my God, you know.
Yeah.
Just it's iterating so fast.
Yeah.
If you think about
particularly the using an end-to-end model.
That's right. Yeah.
Was a big deal.
Yeah. Gen AI, basically. To some extent, you can think that the whole industry iterated on the first architecture, which is ML-based perception only, right, for 10 years.
Yeah.
And we made lots of progress. You know, Robotaxi can be done that way.
Yeah.
But you know, over the last 3 years, we're iterating on. You know, we first bring end-to-end model. Now we're adding reasoning to it. It's really 2 generations in 3 years.
The 2 fundamental technologies that we're building on top of. You know, so of course this end-to-end model architecture is revolutionary. But what differentiates us, and what's going to make it incredibly fast for us to deploy to get to level 3, 4, and level taxis, is the fact that we have a classical stack as a guardrail, as a safety system, and because we have a reasoning system. So the long tail of experiences that are probably not in our data set can still be decomposed into routine type of experiences that are in our data set.
Yeah.
And the car will be able to reason its way through, you know, how to navigate, and so how to operate. And so I really think that between these 2 ideas, no matter what the reasoning system decides to do or achieve, you always have a safety guardrail behind it. And so this iteration system that we have is going to move incredibly fast. Reasoning and guardrailing is going to be just revolutionary.
That's right.
All of our L2++ work, that entire flywheel, you know, collecting data on the road and you know, processing the data.
Now we enhanced by basic Neurac and the Cosmos.
Yeah, good job. Good job. Who knows what a human driver would have done? That's pretty good. Yeah, that entire flywheel is essential.
Yeah. As I said, right, in the model side, you know, closed loop evaluation is so important. We're running essentially, you know, as you know, 2 million tests every day, and they are all pixel, basically, reconstruction of the world. It's just amazing, basically, how the technology evolves.
Neurac is so great.
Yes, that's right. It's so critical. And the Cosmos can be introduced as well, which we are working on basically to add. Cosmos can cover the real rare corner cases, and also it can use to amplify the NURAC. NURAC is just reconstruction, but if you put Cosmos on it, it can change the background, change the weather.
Yeah, you could up-res it.
That's
you
right.
Could, yeah.
That's right. Exactly. Yeah.
The combination of these technologies has
That's
really
right.
been revolutionary.
Yeah. It's probably an accident here somewhere.
Well, they really ought to get one of our cars. Look how beautiful it is. Here we are driving autonomously into San Francisco. You know, this interchange here always gives me a lot of anxieties because there's so many different highways, and you know, if you just miss one, you're going to be gone. You're going to be late for about 45 minutes. And so terrific to do this autonomously. So exciting. You said 10 cameras.
5 radars.
5 radars. And how many ultrasounds?
12.
12 ultrasonics.
This spot actually is can be pretty tricky.
Wow, that's nice.
Because basically there's a lot of occlusion, and when you get on the highway, you know, sometimes the car just stops there, but you don't see it until basically you make this turn. So you have to control speed.
Well, I know this exit very well. I come here all the time. You know, people underestimate how gigantic of an effort it is. You know, you've got to build a chip,
Yeah.
build a computer, and even building the computer that is functional safe. So that you've got the chip, you've got the system itself. The system has functional safety designed
That's
into
right.
it. The software stack, the Drive OS.
software. Yeah. Then every component of even the classical stack need to get to a certain ASO basically level. We're gonna make a lane change here. Let's see how we do it. See, this is how
Yeah, fantastic.
Very human-like.
Yeah, that's so human-like, right?
Yeah. Hard to describe in code.
That's right.
Yeah.
Most rule-based would have had the car completely pass us.
Yeah.
And then we make one deliberate move.
That's right. And that's what one stage, what we call speed adaptation. And we try to, speed up or slow down, try to get in the gap, then start the lateral move, But that's not how human does it, obviously. And, our Maya is just mimicking what everybody else is doing. So it's amazing.
You know, there's of course the AI in the car, but our AI starts with even AIs to curate the data that we collect.
That's right.
So that.
All right, that's an interesting scenario. Let's see how we handle it. Oh, we detect from here. We decide to go to lane change.
That makes a lot of sense, actually, because once you cross the street,
that's right. Yeah.
Once you cross the street, that's not very much distance to stop. And so we're going straight. That's going to be interesting.
So we'll go past them and then do a lane change back, I think. But it's like the whole street
actually
is
makes
packed.
sense.
Let's see how we do this.
Okay. It's blocked on the right.
Yeah.
It's already blocked on the right.
Yep.
And so it anticipated that. And so it moved us to the middle lane.
Yeah.
Yeah. Oh, look at this. This is great.
This will be tricky. Let's see.
We're just about to pass a bus.
All right. Okay.
Yeah, fantastic.
Wow.
That's so graceful.
Yeah.
It's more peaceful than humans driving.
Actually, this is what the media reporters, they feel, right? Safer, essentially.
Yeah, it's confident.
It's confident. It's calm. It's safe.
So we have all the AI models that's inside the car. We have the AI models just to curate the data. Right? We don't want a whole bunch of wasted same thing, to retest it with the same thing. And so you're looking for out of distribution things. You're looking for like circumstances. The
terminology for this is called a functional scenario tree. If you think about it, it's really basically, a bunch of nodes which are the, cases we need to cover. And then we have an AI tool to curate data to fill in these different nodes. And when we see a new scenario pop up on the road testing, then we're gonna create one more layer, right, or one more node on this functional scenario tree.
Yeah. Okay. So this is called the functional scenario tree.
Yeah. So this is a double.
That's really great.
Basically, It's just
so literally
natural.
we crossed the lane, but it was perfectly safe to do so.
That's right. Yeah. You'll see some hesitation sometimes. Like we're definitely, I would say, more conservative than average driver because, for example, definitely will get to at least a moment of full stop in front of every stop sign, which is the right thing to do, obviously. But yeah.
And so we have the data. We have AI models for your functional scenario trees. You have AI models for synthetic data generation.
That's right.
Maybe
and we have AI models for Neural for sure.
Right. We have for drive log to reconstruction.
Right. Yeah.
When you do engineering, you can keep progressing and keep adding more capabilities. Only if the foundation is strong.
Is strong. Yes.
When you're investing all of these new capabilities, but you can only do so with confidence if there's no regression.
Right.
That's really one of the most powerful things about our classical stack. It's so safe. Every one of these iterations, every single month, you're quite confident deploying it into the road. Between the evaluation systems and the validation systems and the methodology and the guardrails.
That's right.
It's always safe. From here on, our velocity is going to be so high.
Yeah. So this is the residential area. So in this area, as I said, bus is a challenge. And then a lot of random parked cars, we call them DPVs, double parked vehicles. And nudge around them is really, really critical.
You got a lot of delivery vans and trucks.
That's right, exactly. Weekends are better, but weekdays, there's just a lot of them. And DPV nudging is also, quite difficult to get right. But the model again is learning, what human does essentially, which is great. But even sometimes human make mistakes. So if you make the wrong decision, you will end up in oncoming lane. And sometimes you get stuck. That's why I think what we are doing in the current implementation is still slightly on the conservative side, because the cost of making a wrong decision is too high.
Yeah. Safety first.
Safety first, exactly. It's okay to get stuck essentially for a L2++ product.
Yeah.
Even L3, I think it's okay.
Yeah, that's right. If the human's in the car.
That's right.
Yeah. That's so great that we got the highest rated NCAP.
I know, yeah.
First time out, it's incredible.
That's right. Okay, this is the right decision as well, because it's oncoming.
Exactly.
We're just patiently waiting, and human might be slightly faster, but I think we.
I don't think so.
All right.
I think I would have done about the same.
Interesting.
NCAP 2025, so rigorous, and the Europe NCAP, the standards are so high.
Yeah. And we got the highest score.
That's crazy. That's so exciting. I knew we were going to pass, but to get the highest score is really incredible.
Yeah, it's again many years of hard work.
Yeah.
Which is also very important because all this work.
But that's our safety guardrail.
That's right. Will be translated into L3 and L4 capabilities.
Not bad.
This all image.
Oh, wow, excellent. That was a
Look
good
at how
speed bump.
comfortable
Oh,
it
yeah.
is, Okay.
Oh, good move. Very nice. Yeah, makes sense.
Yeah.
So some people just drive right over a little pothole. I kind of drive around it personally.
I think we haven't worked on it, but that's a very important feature to have, essentially, especially on highway,
Yeah.
If you don't avoid the potholes.
But what do our drivers do?
Our drivers?
Yeah.
Oh, you mean
just now
you
it would
the data
probably.
collection drivers.
Yeah. I wonder what they do.
I think they will get around it. Right?
You think so?
I don't know. Yeah, we can, but we can
I would
always,
say just now.
Hopefully, some of them do, and we can always select those data, in our fine tuning step. And we can also do reinforcement learning.
Yeah.
Reinforcement learning is very effective. Really have a more capable model, right? This is what we are working on for the next generation, right? I think reason is one thing, and having memory is very, very important. It will need less help from the classical stack.
Yeah. It's so incredible that a billion parameter model can encode and all of this. But I guess in the end, the question is for the car, looking at all these features, what are the salient features it needed to encode? It probably is not that much information.
Right, yeah.
But the salient features necessary to predict the trajectory is probably extremely small.
That's right.
We see a lot in the world, so we are impressed by the amount of information, but how much of it does really necessary to contribute to trajectory prediction is probably very, very small.
Very small, yes.
It's so great. Yeah. It started to turn before the car even passed us.
Yeah. That's what the model does.
That's what people would do.
That's what people would do, yes. Channelized cone, Jensen. We set it up all for you.
That's so great.
Channelized cone is also amazing with the model because it's so hard to get it right with the classical stack. You have to kind of generate lanes from cones.
Right. I would have zero concerns doing my email all the way through San Francisco, How nice is that, right? Nice. Very nice. Wow, what a great drive. The Alpha Mayo AV stack drives very much like a human. It imitated a human and generalized incredibly to all these different scenarios. And the classical AV stack gives us the safety guardrails that has been fine-tuned and tested, and with all of the engineering rules that have been put into it, gives us incredible safety. And so when we were driving, the two of us were just talking, enjoying San Francisco, and it was just incredible. This is the way transportation should be like.
That's right.
100% comfortable, 100% confident, and completely revolutionary.